Hi, Matthieu. Hello. How are you? Very good. And you?
区别好。Yeah. Hey. Yeah, thank you for showing up, everyone. Yeah. Okay. So let's maybe it's exactly 2:30, right? Yeah. So we're extremely happy to have Matthieu Le Tacon to give a talk on the barium nickel to arsenic 2. We actually have a theme. This semester, trying to understand more of the topic of the barium nickel to arsenic 2. And the first talk was given by JP Paglioni, and actually raised a lot of questions. So I'm hoping this is new measurement, which I saw published in Nature Com by Matthieu, will shed some light on this. Okay, so it's all yours.
Okay, well, thanks a lot, Peng Cheng, for inviting me here. Yeah, I couldn't attend GP's talk, but I watched it online as soon as he was available, and yeah, I realized there were a lot of questions that were asked to him, but directed to us. So I somewhat tweak a bit my talk so that I can answer some of these things. So yeah, that's going to be a talk about this nickel 1-2 compound. And oops, let me just first start acknowledging many people, and I probably forgot some. So sorry, I just want to use here the laser pointer. How do I change this to a laser pointer? Okay, whatever. Okay, this will be a mouse.
Yeah, so, your cursor is fine. The cursor looks fine. Yeah.
Yeah. I know. I think this is this one, right? Laser pointer. Oh, great. So I want to acknowledge first all my colleagues. So this is a work that was largely done within our institute in Karlsruhe, the Institute for Quantum Materials and Technologies. So we got the single crystal growth for that particular project by Amira Gigerat. The Raman experiment were mainly done by Yi Yao, graduated some time ago already now. And with help of Tom Lackman, who was also very highly involved in X-ray measurement, together with Michael Assouliou and Michael Mertz. We have Mehdi Frachet, Christine Villa, and Christophe Mangas, who have been doing transport and thermodynamic measurement, as well with Liran Wang and Frédéric Hardy, which I have not written down here, sorry for that. And the series report of Rolf Heid and Roland Villa, and most importantly, Jörg Schmalian. And here, what you cannot see below is this thing is the contribution of Alexei Bossak and Luigi Pasolini from the European Synchrotron Radiation Facility for X-ray measurement. Okay, so that's a rough outline of my talk. I mean, I'm starting with a bias introduction to that interesting system, and how I got into that. I talk about Raman scattering result in the first part, and then I will talk about our inelastic X-ray scattering result and the insight about the I-CDW formation in the second part. So first, how I got introduced to that system. So basically in 2018, well, the paper of Peter and John Pierre appeared on the archive January 18, something like that, and then showing that it was in this non-magnetic analog, say, of the iron wave superconductors, charge density wave and superconductivity. And basically the week after, Michael Mertz from our institute came to me and says, well, you know, that's an interesting system, and we do actually have some data as well here on the phosphorus dope compound. So the paper of Peter was about the cobalt doped and the iron doped, I think. And there in Karlsruhe we had data on also on the cobalt doped, iron doped, and phosphorus doped, showing also this kind of charge density wave. And basically, Michael asked me, well, do you think with your techniques this could be something interesting to look at? So my techniques, I'm going to show a bit, to discuss a bit about that, is mostly inelastic scattering. So typically phonon spectroscopy, and generally when I hear about charge density wave in a superconducting system, yes, I find this quite interesting. So the nickel 1-2 system, I'm just going to repeat things that John Pierre has said the other day. So this is it's a 1-2 typical crystal structure material. So it's a tetragonal system, and as you cool it down, it was basically known from already in 2012 and maybe even before that they had a strong structural distortion. So first order transition to a triclinic phase. And of course, as anyone, we all love crystals, but when we see a system going to triclinic and has a very low TC, well, that might not be the first choice, the most exciting one to look at. I prefer things which are a bit structurally simpler. At least I prefer. And then, of course, when this incommensurate charge density wave came up, I mean, it started raising some questions about, first, why is TC so low compared to the iron-based? And then what happened to TC when the charge density wave is suppressed? So basically, this triclinic phase, when you dope the system either with cobalt or with potassium, phosphorus, sorry, is rapidly decreased. And when it's completely suppressed, there is a strong increase of TC. So it goes from 0.6 Kelvin to something like 3.5 Kelvin. And then the question is a bit what happens to this incommensurate charge density wave. So again, charge density wave and superconductivity. I mean, I think it's been seen now pretty much all over the place. I mean, we found this in the cuprates a few years ago. But if you look back in the literature, this is already the case. It's already present in alpha uranium. It's present in decalcogenide. It's present now in this newly discovered Kagome superconductor. So it seems to be really ubiquitous that you often have charge density wave phase next to a superconducting one. And in the particular case of this nickel 1 to 2, the fact that they share the same structure with the iron-based superconductors, so really draw the parallel and ask the question of whether they were a non-magnetic analog of this system. And with this, it raises the questions of basically, given that in the nematicity and electronic nematicity is proven particularly important in shaping the phase diagram of the iron-based compound, and given that this nematicity is basically rooted in the fact that you have doubly degenerate spin density wave at q equal pi 0 and q equal 0 pi, and because, as I understand Jorg correctly, nature doesn't really like this kind of degenerate state, and so the nematicity or the nematic fluctuation arise to try to lift the degeneracy between these two degenerate magnetic order. So in a sense, if you have this nematic fluctuation that occurs when you have a spin density wave, doubly degenerated spin density wave, when you do have possibly a doubly degenerated charge density wave with wave vectors which are pretty similar. So instead of being pi 0, 0 pi, now it's incommensurate, and it's close to a quarter, say 0.2800 and 0.280. These are the wave vectors at which the superstructure peaks are seen. You might wonder whether there is some nematicity associated with it. And as I was asking myself that question, basically there was this paper from the group of Jean-Pierre who came out showing that indeed they were in the strontium-based compound, strong nematic signal to be seen in the elastoresistivity and possibly enhancement of the TC related to this nematic fluctuation. So the difference with the iron-based compound now is that the symmetry of the fluctuation is a bit different. So it was B2G in the iron base and it's P1G now in the nickel base. Okay, so there's been a lot of papers in the last 2 years on this compound. I mean, I wouldn't say this was the most published system, but I think there's quite a decent amount of paper that came out, and also recently. So please don't be upset if I don't cite yours in particular. Again, trying to give here somewhat a more personal view on the system. A question that was asked in Jean-Pierre's talk was basically related to our claim, or to the Karlsruhe claim, so to say. It was not my claim, actually. This was really from Michael and Christoph Meingast, that there was a small orthorhombic distortion taking place somewhere above the triclinic transition in the system. And evidence for that were reported in that paper, and this is based on a high-resolution thermal expansion measurement. So basically, what Christophe does is that he looks at the change of the length of the sample as upon cooling, and you see that when you go to the Trichnik first-order transition, there is a huge change. I mean, relatively large change, say, of the 100 direction against the 110 direction. But if you zoom in, you see a very tiny difference occurring just above. So upon cooling, it's at 142K, and that would look more like a second-order transition, because the first one looks first order. And of course, it's a very small effect on the parent compound, but if you dope the material with a bit of phosphorus again, I think it becomes really more obvious. I mean, this looks first really second order now, and the amplitude increases a bit with that doping. So well, there's been further work on that, and I'm not going to detail that, but I mean, this is recently put by Christophe on the archive. And so we carried out a more systematic thermodynamic study of the phosphorus doped system. And now this is for a compound which is close to 5%. So you see in the thermal expansion, a lot of things going on, but in particular, you see, if you look at the thermal expansion along the 100 direction, you see a clear peak here, which is did with the orthorhombic distortion. And actually, from this measurement, you can actually directly extract the orthorhombic order parameter, and you see that its amplitude is of the order of 10 to the minus 4. So to fix idea, I'm going to show that a bit after, but that's literally more than one order of magnitude, or at least an order of magnitude smaller than what you have in the iron-based system. Now, what's nice in that study, I mean, you also have specific heat data, and you can see that there is a peak in the specific heat. So it's a very tiny peak, which is associated with this orthorhombic distortion. So you can really see that it's an actual phase here. Okay, but again, this is on the dope system, and we've seen that the doping, the phosphorus doping, tend to increase this order, and it remains very hard to see on the phosphorus doped. Now, there was a question also last time on whether there were some signature of such orthorhombic phase in the diffraction, and that's not an easy one. So I just took this as an example. I mean, this is paper from Tonegawa et al., which was basically looking for distortion in uranium, ruthenium-2 silicon-2, but it's pretty much the same space group we're talking about here. So you go from the tetragonal phase, and then they discuss whether you would have a distortion to the FMMM space group or the IAMM space group, which are two possible orthorhombic distortion. And the first one, the FMMM, is really that you see in the iron-based case, whereas the IMMM, from group symmetry point of view, would be the one that we're dealing with the nickel case. So in the phosphorus dope compound, if you want to see this diffraction, you have to go. So you see you have this twinning effect. So you basically see from the twinning, you see a splitting of the different Bragg peaks, and the splitting is basically increasing as you increase the order of the reflection. And so to see something, Tom Lackman, there is his master work, he basically had to go to fairly high index reflection. So this was done on a 4-cycle diffractometer, and that you see that at around 100K in this doped system, so just above the Trichnik transition, you do see that the Bragg reflections are not round anymore. I mean, you see this kind of splitting, fourfold splitting of the 800 reflection, whereas the 488 reflection now is more spreading along the diagonal, which is exactly what you expect for this kind of IMMM distortion.
So did you see temperature dependence of these peaks? I mean,
this is very, very small effect actually, and this is, I mean, all this discounting took a lot of time. So we had some scan as function of temperatures. Okay, some cuts only. We don't have the full maps as function of temperature. I mean, this was done on the 4-cycle diffractometer at home, and it took an humongous amount of time to get those. Okay. But yes, we do have some scans that were done as function of temperature. We see the broadening. The bottom line is that if you really look at the parent compound, it's really, really hard to resolve this kind of splitting on the 4-cycle. On the dope compound, I think it was quite convincing, but it remains a very, very tiny distortion. And I emphasize that because, well, it was discussed last time, but that's also going to be important for the rest of the story.
Thank you.
Okay, so I think back then, I mean, there was this question even in Karlsruhe. I mean, we grew somewhat convinced that there must be this autonomy distortion, but we were wondering whether there would be some other ways to see it, maybe more direct. And then, well, that's where I came in. So I'm doing mostly a scattering method. So most people here are probably familiar with it, but just in case, what we do is we take some incident particles, so typically photons, and we shine them onto an interesting system, which we bring from an initial to a final state. And during the scattering process, the particle changes direction, so its momentum, and its energy eventually. And so we do have a scattering triangle and conservation law. So we have to conserve the energy and we have to conserve the momentum. And depending on the energy transfer we look at, we can investigate static correlation. So that's pretty much what we do in the diffraction experiment or the dynamics at finite energy. And at zero momentum transfer, we probe homogeneous correlations, and at non-zero Q in homogeneous correlation, otherwise, as I said, the dispersion of the excitations. So I do this in that particular case. We investigated these samples with two methods. So first, Raman scattering, which is inelastic scattering of visible light. So we typically have laser energy, which is red or green, so 1.5 to 2.5 electron volt, and a wavelength which is much larger than the lattice parameter, so the visible range. So so that means that we have a probe of the system at Q equals 0. The energy resolution is very good. I mean, it's like 0.1 milli-electron volt, and we do have selection rules which allow us to assess the symmetry of the excitation, and as well some case-space selectivity for the electronic excitation. That's typical spectrometer. It fits on the table, and that's kind of typical spectra. So what we measure is the Raman response. That's basically this scattered photon intensity as function of the energy loss of the photons. And we do see a continuum of excitations and some phonon lines and some magnetic excitations. So we can assess the nature of the excitation as function of the selection rules, for instance. Now, the second technique I'm going to use a bit later in the talk is inelastic X-ray scattering. It's conceptually exactly the same thing, except that now the photons have essentially 10,000 times more energy. So to be able to discriminate the scattered photon as function of their energy, you need a somewhat much larger instrument. So we do that at synchrotron radiation facility. So here's a scheme of the beamline ID28 at the SRF. So that's basically a very long spectrometer. I'm not going to enter the detail. What we get is typically an energy resolution of 1.5 to 3 milli-electron volt. So it's not much as good as for the Raman scattering. But the big advantage is that because of the short wavelengths, we can cover many Brillouin zones. And this allows us to select also, to give us some selection rules, some contrast between the different Brillouin zones to investigate phonon, with given polarizations. I mean, we basically picked up the phonons as function of their polarization, and we can choose basically from the scattering geometry which phonons we want to study. That's going to be important for this. Okay, so I'm going to start with Raman, and coming back to the story of whether this nickel wanted to exhibit an orthorhombic distortion or not. I mean, I recalled that well, in the early days of the iron-based superconductors, there were some phonon studies, and there was a nice work by the group of Yann Gallet and Anna Sakito in Paris, and where they studied the phonons in the cobalt dope iron 1 to 2. And what they see here is in the signal, I mean, they see the in-plane polarized mode, so the EG mode. So when you're in the tetragonal phase, the EG modes are completely degenerate because well, the vibration of the iron or arsenic atoms in the plane have the same energy if they vibrate along A or along B, essentially. So this is doubly degenerate. And then when there is the formation of the charge density wave, of the spin density wave, sorry, and the orthorhombic distortion associated with it, well, you split the mode, you lift the degeneracy between the two EG modes, and you end up with a B2G and a B3G mode in the orthorhombic phase. Now, the splitting that they observed was quite consequent. I mean, it was actually something like nine wave numbers. So they follow it as function of doping and temperature. And it was quite a sizable splitting. Actually, they note in that paper that splitting is in fact much too large to be accounted for by the structural distortion. That being said, I asked the other day, I mean, we did have some data. So this is the thesis of Anna from a few years back, and they've also measured in the iron 1 to 2 the structural distortion. So really the orthorhombic, the amplitude of the orthorhombic distortion. And I thought like, well, we can compare that directly with the EG splitting of the phonon. And if it put these two things together, I was really shocked. It works very well. So the EG splitting is directly a measurement of the amplitude of the orthorhombic distortion, if you like. Now, again, this distortion here, I mean, the splitting that they see compared to the distortion is about an order of magnitude too large. And back in 2009, I don't think there was still already a lot of discussion about nematicity, but in the end, what it means is that this whole splitting is enhanced by the nematic ordering. Okay, so at least this is how it's understood now. Nevertheless, my first thought was like, okay, there is a splitting which is at least an order of magnitude smaller in the nickel 1 to 2. So if we have a splitting which is 10 wave number in the iron-based compound, maybe in the nickel base, we should be able to see a splitting of the order of 1 wave number, something like that. It's a very small effect, but it should be possible to resolve it. And even if it's smaller, we should at least see a broadening of the line.
So in
the
cobalt barium 1 to 2, the EG splitting, does it change anything across TC, or it's not known?
Across
TC, I mean the dope sample.
I don't know. I'm not sure whether this was looked at carefully, simply because I think it was most of a curiosity, but I'm not sure they pay attention to that. I mean, if you look here, this was done carefully at the 4.5% level, and they didn't really went down to very low temperatures, and also, I mean, back then the quality of the data which I show, I mean, it's it's I mean, the EG phonons are something which is not so easy to measure, because you need to take your sample and to measure it from the side with the polarization along the z-axis and things like that. So it really depends, and typically here this is a byproduct of the measurement. It was not the main focus of the measurement, I would say. So I don't think this has been looked at very carefully.
Okay, thank you.
Simply because you see the distortion in another manner, so it was just not so. It's a kind of side effect. So nevertheless, we tried to do that on the nickel 1 to 2, and so we looked at the phonon spectrum. So we measured the Raman spectrum, and we found the 4 Raman active phonons. So there's a A1G mode which corresponds to vibration of the nickel atom along the c-axis, the arsenic mode which has the B1G symmetry, and you get the 2 EG phonons that you see when you put your polarization, so cross polarization, on the edge of the sample. So that's why it's a bit tricky, because normally these samples are not very thick. So, well, just first thing, I mean, we note that the EG phonons, they are nice there, but it is somewhat already quite broad. I mean, that was a bit surprising, given that the quality of the crystal that are grown by Amir was absolutely excellent. But okay, we looked at this, and then when we cooled down the sample across the triclinic phase, well, then we have the commensurate charge density wave and the triclinic distortion, and then there's a lot of new peaks coming. Okay, so there's no doubt when you're in the triclinic phase, you're in the triclinic phase. That's clear. And then when we got interested ourselves of what happens in the above the triclinic transition. So we first look at the A1G phonon, and you see that this mode is sharpened and it hardens as we cool down. down to 135K, something like that, just above the tricking transition. And that's exactly what you expect for a well-behaved phonon. Now, when we look at the EG mode, what we see that it's broad, and first you see that it softens upon cooling, which is normally not supposed to happen because the lattice, gets stiffer and the phonons tend to harder. And then clearly it broadens and it splits. Well, it splits, so that's the moment where I say, well, yeah, okay, good, the phonon splits, so that should be orthorhombic, and that's where come this wait a second moment. Just there's something strange here, which is like, if I go back and compare to the area we wanted to, I mean, I told you with this 9 wave number splitting was already very large compared to the structural distortion. And now I have a 20 wave number splitting. So a splitting which in absolute value is already twice larger, whereas a 310 to the minus 4 delta is what I find, what Christoph measures in the doped compound. So where the orthorhombic distortion is significantly larger than in the parent compound. So I'm there now with my parent compound, which has this very tiny distortion, and I have this insanely large splitting of the mode. And if now I take into account the fact that the mode is much softer to start with, I mean, that's almost 50% of the mode frequency splitting. So that's absolutely unacceptable. But that makes it interesting. And that's what gets us to the first part of the story and how we got to the notion of a nematic liquid in that system. So again, we've been comparing that very carefully with the thermodynamic measurement, because this is the point where we got a bit nervous. I mean, at least I wanted to know exactly what was going on where and how to compare this effect with the onset of the charge density wave, with the onset of actual phase transition. So what was going on there? And clearly we nicely see the trickling transition. It was well aligned with the thermodynamic measurement, but what we find is not only that the splitting was very large compared to this orthorhombic distortion, but clearly above the orthorhombic distortion, the splitting was already there. So the onset was much above that. And that was probably the most shocking part. So we decided to go and to check what was going on then on the phosphorus dopes, and we looked at the whole series and we compared in somewhat systematic fashion. So we measured the resistivity and the derivative of the resistivity. We looked at the intensity of the incommensurate charge density wave and of the commensurate charge density wave as function of doping here. What we find is that this splitting of the EG mode remains here up to 10% splitting. So we still have a very, very nice splitting here. I mean, the 7%, I mean, the splitting is up to like 60% of the mode frequency. The second EG mode, which is a bit weaker at higher energy, we don't really resolve the splitting, but I mean, it clearly broadens as well. I mean, so it feels something as well. And again, if we try to compare that with the different phase, for instance, with the onset of the CDW, it's a bit disturbing, because if you look carefully, I mean, the mode split, but the mode is very broad to start with. And I mentioned it starts to soften upon cooling, and then it broadens and splits. So the onset of the splitting, if you like, in a sense, can be seen with the beginning of the broadening of the line. So and that broadening is occurring at very high temperature, at temperature much higher than that of the where we can detect, for instance, the CW satellite. I mean, with X-ray tube at least. So this has been extremely puzzling. So we measured the whole series, and then we put this into a diagram, and that's what we found. Huh? So we nicely see where the trickling transition is taking place. We measure superconductivity. I mean, Christine Villa did that with specific heat. So nicely the superconducting state. We do have then the signature. We thought was the signature, at least, of the orthorhombic distortion, maybe in the resistivity, and there was a kind of minimum in the resistivity, which at least in the parent compound and at low doping seems to be well aligned with the with the thermal expansion. It's a bit different at higher doping, but if different, if there is an atomic distortion here, but it's actually below the minimum of the resistivity derivative. So anyway, the bottom line is that this onset of the broadening of the phonon is occurring at much higher temperature, and then what's the question of what's going on here? Because we do have a tetragonal phase, and in this tetragonal phase, well, we do see a massive splitting of our G modes.
So basically, you're seeing optical phonon split from 1 to 2, right? Even way broadening, even way above. Have you seen that with X-ray scattering as well? Because then you can determine its wave vector dependence.
Yeah, I'm going to there to that in a moment.
Yeah.
I mean, if you want a spoiler, rapid spoiler, there is a soft phonon which is associated with this charge density wave, and the soft phonon is basically this phonon. Okay, at finite Q. So that's this mode that gets completely soft at the wave vector of the charge density wave. So everything's connected in a way.
Thank you.
So, but that's the point where I went to see Jörg Schmalian, and I said, well, look, I have this, and now we will. It's quite clear. I mean, we do have on the one hand Christoph, who is the official authority in Karlsruhe to tell us when there is a phase transition or when there is no phase transition. And it's fairly clear. There's no phase transition at this temperature in this compound, and yet we do have this splitting. Our X-ray specialist Michel tells us that at that temperature, well, the system is fairly tetragonal, and we see no sign of the splitting of the line. So we do have a tetragonal system, but we do have a massive splitting of the EG mode. What's going on? So Jörg is very smart, and then he look at me and say, well, there's no splitting. Well, it took him a week to say that, but that's the way of saying it. and basically what he came up with the idea that indeed you could conceive a situation where your EG mode, your doubly degenerate EG mode, can couple to fluctuation of a certain symmetry. And turns out that the B1G symmetry is the right symmetry to couple to this EG mode. And that might give rise to an apparent splitting without lifting the degeneracy. So that was his intuition, and basically he came up with a toy model. So he said, well, you take a 2 degenerate phonon, and you couple this to an Ising variable which describe a nematic degree of freedom. So in short, you do have this operator here, this polymatrix, which describes basically 2 states, and there would be this two orthogonal atomic distortion. So you call that the spin up, and you call that the spin down. You can have a coupling constant of this distortion with the phonon mode. So that's this lambda constant, and then you put in some fluctuations. So that's basically a tunneling rate between the 2 configuration at a given frequency omega. And so what's nice in that model is that it's a non-trivial many-body problem, but it turns out that it can be solved analytically. So you need a smart postdoc to take care of that, and that's Roland Villa. Who did a great job in solving that problem, and also at finite temperature. So I'm not saying it's easy, but I mean, I think he really enjoyed that. I mean, there's a lot of nice math. And then you can compute this, and what you find is that the spectral line corresponding to the Green's function corresponding to your doubly degenerate form can actually split if you are in a regime of relatively strong coupling, but not too strong. Otherwise, you basically induce a structural distortion. And so that splitting can obviously occurs if you have a nematic order. So that means if the expectation value of your polymatrix tau z is 1. But again, in this strong coupling regime to nematic fluctuation, you can have this splitting even in the absence of a nematic phase transition, even if the expectation value of the nematic order is actually 0. So in that case, you do still have technically a degenerate EG mode, but you do have a splitting of its spectral shape. And that bears, according to Jorg, a strong analogy with the spin liquid problem. So that would be a Z2 spin liquid problem, if you like, which yields us to call that phase a nematic liquid, so in analogy. Now, it has also a few implications, and the first one is that, well, if you do have some kind of nematic fluctuations, they should be visible with electronic Raman scattering, and because we said that those were most likely to occur in B1G rather than in B2G, well, with Raman scattering, you have selection rules, and you can measure the electronic Raman response in the B2G channel and in the B1G channel. And as a matter of fact, there is a very weak temperature dependence in the B2G channel as you cool down from the electronic response, and quite clear enhancement of the response at low frequency in the B1G channel. So that enhancement, that being said, I mean, the response is extremely broad, okay? So there seems to be strongly overdamped, which suggests indeed that this electronic degrees of freedom, or this electronic response, strongly couples to something, very likely to the lattice. But at least it has the right symmetry to couple with the EG phonon, so this was good news. And the second is that opposite to the iron-based superconductors, should not be possible to detwin the sample. So if you know that if you stress the iron-based superconductor, so here in that case, this is the iron selenium. So these are the data from Yuan Li. If you do Raman scattering, so if you apply some stress on the system, instead of seeing your two mode, B2G and B3G, you see either one or the other. So you can really detwin the system, somewhat have domains which are aligned only in one direction. You can probe that. Now, the way we try to do that here in the nickel-based compound is to use this fiberglass substrate, so that provides some kind of anisotropic that it's have an anisotropic thermal expansion. So we glue our nickel 122 sample on that, and we do the Raman measurement, and we see what happened. And what happened is that basically we do see a small redistribution of the spectral weight, but we are not capable of getting a fully polarized nematic state, if you like. And the reason being that we cannot detwin the system because it's not order, right? So it's like if you try to, I mean, you do break the symmetry with your external strain field, but there's nothing to detwin per se. Good. So the conclusion there is that the large EG splitting that we saw is purely dynamical in nature, and that we're dealing with some kind of funny electronic nematic liquid state in this compound. Good. That takes me to the second part of that work, which is related to the charge density wave. So there's a charge density wave, there's a nematicity, there's all these things, and all this must be connected. And we thought it would be also quite relevant to look at the phonon dispersion to try to understand the relationship between the orthorhombic distortion on the one hand and the charge density wave, in particular the incommensurate charge density wave on the other hand. So for this, again, we first started doing some calculations. So I mean, okay, in previous version of that talk, this was inverted. So what we did is, I mean, the kind of systematic way we do that is that we do have first nice crystals. Then Michel is making a very detailed crystal structural refinement of those crystals, and using the lattice parameter, the experimental lattice parameter. Our colleague Rolf Hyde is calculating the dispersion of the phonon. And I think in contrast with early calculation of this on this compound that were maybe not done precisely with the right experimental lattice parameter, and probably also not with the right Z value for the arsenic, maybe with the relaxed value here, if you use the actual experimental lattice parameter, what you do find is that this tetragonal structure is actually unstable. So you see a very nice, clear softening of a mode. And if you look carefully, that mode So it's softened at finite Q. So in the calculation, the instability is close to a quarter. It's really close to the experimental value. And what you find is that if you follow that branch, it's actually a doubly degenerated branch at the gamma point, and this actually happened to have the EG symmetry. So the branch which is getting soft is in fact the same branch which is splitting in the Raman experiment. So that's the weirdo. What's already interesting to notice here is that, I mean, Rolf can also calculate the electron-phonon coupling, and you see that the widths of the peak here, the red widths, represent the contribution to the electron-phonon coupling. And this mode exhibit a bit of electron-phonon coupling, but it's far from being the dominant channel. I mean, the dominant channel is clearly that guy, and this actually is the A1G mode. I haven't shown that, but if you dope the system, it actually shows and displays a nice little Fano asymmetry, which is in line with the notion that this is the most, this is the main contributor to the electron-phonon coupling. So that guy is not the one which has the strongest electron-phonon coupling, yet it displays a clear instability. So what we thought is we wanted to investigate the dispersion of that mode, sorry, I made something stupid here. Yeah, sorry. Before that, so we made use of a very nice option of the ID28 beamline, the X-ray scattering, which has a thermal diffuse X-ray diffuse scattering station next to it. So basically, what you measure here is kind of a diffraction experiment that you mostly saturate your Bragg reflection, and you can look at the diffuse scattering between the Bragg peak, and that happened to be extremely useful to find your way in the reciprocal space. So in other words, what you do here is an inelastic X-ray scattering experiment, but you integrate over the scattered energy. So that's the inelastic X-ray scattering cross-section. So there is a Bose factor, there is a structure factor. So basically telling you that the more electrons you have, the better you scatter. There is a selection rule, so telling that you have to align your momentum transfer with the polarization of the phonon if you want to see it. And there is a delta function for the energy selection. And the diffuse scattering is basically telling you that if you see some diffuse scattering signal, so that means that you do have normally, possibly soft phonon. So that doesn't work each time. I mean, you also have some static defects, but often when you have some diffuse scattering, you actually see it actually corresponds to soft phonon. So the strategy is to map the reciprocal space, find out where there is a lot of diffuse scattering, and then go there and to do an inelastic X-ray measurement to see whether it corresponds to a soft phonon or not. Okay, so we run some structure factor calculation, and that tells us that the best place to look at the soft mode would be next to the 411 zone center. And that's where we decided to go and to take some temperature dependent diffuse scattering. And that's how it looks like. So here I show you some cuts. So this is the 411 Bragg reflection. And this is the HK plane, and this is the KL cut. Okay. So at room temperature, we also really nicely see a very beautiful diffuse scattering signal here. So there's a fantastic detector. There's basically no background. And you see that already at room temperature, you have a nice diffuse peak. If you look in the KL plane, you see this nice diffuse satellite around the Bragg reflections here along the so that would be the 4-1L series here. And then you see this nice diffuse satellite at 0.28. As you cool down the system, I mean, the intensity of the satellite increases, and eventually it becomes as strong as that of the Bragg reflection when you're getting close to the trickling transition. So we've been looking at this a bit more carefully. So here you do some cuts in the reciprocal space. So here are cuts along the so 4 0.72 L. So that means at the in-plane wave vector of the instability and cut along L. And that's how the intensity look like. And that's a log scale. And I found this very instructive. So you can fit this very nicely. And basically, at high temperature, you can just fit that with a Lorentzian. Okay, so that's what you expect for diffuse scattering from a simple fluctuation, so to say. But as you cool down, you see that at low temperature, this is not a Lorentzian anymore. And actually, what you do have at the below roughly 146 Kelvin, what you do have, you have to fit this peak with a combination of what is called actually a super Lorentzian. You have to fit this with a Lorentzian for the diffuse background and a resolution limited feature that corresponds to actually a long range order Bragg peak. So in other words, you can see from the diffuse scattering really nicely the difference between, well, the fluctuating part and the long range order part. So we could analyze this very nicely. So you have the width of that Lorentzian here is inversely proportional to the correlation length. And what you find is that the in-plane correlation length is increasing slowly as you get towards low temperature, but it's not really critical, I would say. It's almost linear, kind of funny manner. But along the c-axis now, the inverse correlation length increases much more dramatically and exhibits here some kind of critical behavior. And if you look now simply at the peak intensity, okay, so really at the intensity of the peak here, how it increases, you really find that it shoots up pretty much at the temperature at which the correlation lengths along the c-axis tend to diverge and corresponds to the long-range order, which relates to the anomalous C over A behavior that Christoph sees in the thermal expansion. Now, if we look at what's going on here in the thermal expansion, you see that this temperature at which the intensity strongly increases corresponds to the downturn of the thermal expansion, which is just preceding the orthorhombic distortion. So in other words, it looks to me like the long-range CW order forms, and just below, then the system exhibits the orthorhombic distortion.
So we also look like a first-order transition or second order?
A second order.
Okay. But your in-plane correlation does not diverge, right?
I mean, what you mean doesn't? I mean, it
yeah,
becomes really. I mean, it becomes kind of resolution limited. You know, it just can't see it anymore. I mean, it's okay. That's a good point. I mean, what I'm plotting here is really the fluctuation. So that's really the Lorentzian width, okay, of the fluctuation part. And then at that point here, or below that temperature, what I do see is a resolution limited Bragg reflection on top of the diffuse background, if you like. So, well, I don't know. To me, it looks like it's diverging, but we can discuss.
But there's no Curie West-like tail, right? It goes directly. It seems like it goes to 140 some Kelvin, then directly happens. Not like your standard second-order phase transition. You'd expect a long sort of Curie West or whatever the fluctuation regime.
I mean, this looks pretty much like I mean, that's K-1, right? I mean, so it just follows this functional part. I mean, so it looks pretty much Curie-wise to me, right? Okay, we can
discuss later. Yeah. Okay.
Yeah. Just to say a few words about the phonon. So we did this measurement with the resolution that gives us the largest flux, like at the 3 milli-electron-volt, and that's the phonon spectra, how it looks like. So we nicely see some well-defined phonons here. So we can fit this. Actually, the solid line below are actually really the fit to the data. We can extract from that the dispersion of two modes. sorry, the contour plot here is the calculated intensity for the soft phonon. So the calculated the intensity, the structure factor calculation. And so I'm not entering the details of the fitting procedure, but basically we can constrain it quite severely so that we're capable of distinguishing what is really the elastic contribution and the phonon contribution to this fitting. And what we find is that the elastic line has some kind of a maximum at the wave vector of the instability. The mode is getting a bit softer, the low energy mode here. So that's at 250K, so above, well above the transition. And there's also some kind of broadening around the wave vector of the instability. Now, if we cool down, what happens is that the intensity at I-CDW is increasing tremendously. Okay, so we do have a lot of elastic line here, and below 160K it basically becomes impossible to measure because this intensity becomes too strong. But if you plot that on log scale and normalize thing, what you clearly see, I mean, you get the phonons here, and you see that there is a phonon which is soft but not completely soft, and that it's getting softer and softer as you cool down. A way to quantify that is to plot the half-wave maximum, for instance, of this profile, and you clearly see that it decreases while the intensity just shoots up here. So it's really, really hard with that resolution to actually come with a quantitative analysis, and mostly because the phonons, as we fit it already at room temperature 250K, it's already broad, you know. So you do have a low energy feature at around 4 MeV, which has a damping of about 2 MeV, and it is on top of that with a resolution of 3 MeV. So basically, it's very, very hard to get quantitative as you get closer to temperature. But it's quite clear that there is a soft mode which is associated with the CDW formation. Now, I'm just going to highlight this recent work from Birgeneau and colleagues, where they did same kind of measurements, so inelastic X-ray scattering, but with higher resolution. They went to spring height, 1.5 MeV, and there basically, by looking carefully, what they claim is that the phonon get completely soft first, so and you actually end up with having an overdamped soft phonon already at 160K. So that's the point where I cannot measure anymore, and that the static CW order, so really the divergence or the apparition of the Bragg reflection associated with the CDW order, is occurring well below this temperature. And so that somewhat decouple these two things, and that the elastoresistivity signal, which has been seen by John Pierre's group, but also by our group, by Mehdi Frachet. So I'm just flashing this. So this is an advertisement for the talk of Mehdi, which is going to be in this series of seminar in a few weeks from now. So where he will discuss in more detail the evolution of the B1G elastoresistance in this compound, and it's clearly associated with the formation of the incommensurate shortness wave phase. Okay, so just to finish a bit here, I mean, we do have in our toolbox a few tricks to find out the origin of the softening and whether it's a normal Chernusky wave or not. And you can calculate, for instance, the joint density of states, and you see that there's no peak in the joint density of state at the Q of the wave of the instability. You can calculate the total phonon line width. So here I mean, it's really the contribution to the electron-phonon coupling of all the phonons. So not specifically the soft one, all of them. I mean, but we've seen that the soft one is not the main contributor anyway. And you see that there's no clear maximum here, and you can divide the electron-phonon coupling, so the width by the joint density of state. And what you find here is some kind of broadish maximum of this ratio around the Q of the instability, but nothing that looks like a diverging a feature. So there's no particular enhancement of the electron-phonon coupling at that Q. So it is pretty mild, and that indicates fairly unconventional nature of the Chernusky wave. More recently, I mean, sorry, a bit before, we had a nice collaboration with the group of Densa in Mainz, and they actually did a time-resolved infrared spectroscopy, so reflectivity. Time-resolved reflectivity, sorry, to look at the collective excitation associated with the charge density wave. And so they measured it in the triclinic phase, but basically as function of temperature. So in the parent compound, so this appeared earlier this year in the communication physics. And the bottom line is that what you see are collective amplitude mode of the I-CDW, which confirm that these periodic lattice distortion are really a charge density wave in nature. But what they find is that there is a very smooth evolution of those excitation across the different phase transitions. So in a sense, you go from the incommensurate charge density wave to the commensurate charge density wave continuously. And when the commensurate charge density wave forms, then it distorts the system. It triggers the triclinic distortion in a sense by pulling things along the c-axis, if you like. That's how I understand it. But the funny part is that it shows an exceptional resilience against perturbations, meaning that they change the fluence and they always find that they are not able to destroy the charge density wave. And they again concluded there that the CW is highly unconventional in nature. So final comment maybe about the nature, because in the paper of Michael Merz, so there was diffraction, there was and thermodynamic measurement, but they also carried out X-ray absorption at the nickel LH. And one interesting finding is that when they cool the system down across the triclinic phase, well, they see a very strong transfer of the spectral weight from the T2G orbitals with the out-of-plane character to the one which has the in-plane character, from the DXZ or DYZ orbitals to the DXY one, but that this spectral weight transfer is actually already present in the high temperature phase. So it's already present in the possibly in the autonomic phase or in wherever the CDW forms. So on the other hand, one mentioned that a good candidate in the Raman scattering to couple with the EG-phonon was an object which has the B1G symmetry. And turns out an object that has the B1G symmetry is an orbital polarization, which would be the orbital occupation difference between the XZ and the YZ orbital. And so that altogether, I think, suggests that the charge density wave we are dealing with here has a strong orbital character, so it's probably orbitally polarized. So that definitely deserves more investigation, and I'm sure we're not the only one doing that. And that's pretty much where I wanted to come with that talk. I thank you for your attention.
Yeah, thank you, Matthieu. Yeah, very nice talk. So this phonon softening that you see, I mean, what's its doping dependence? The X-ray scattering data.
You have to invite me next year.
Okay, we'll do. So there's a question by EMR. I mean, basically saying that the EG and the B1G are two different symmetry channels. Why are they coupled? Why can they couple?
That they can couple. I mean, okay, May is now doing postdoc with me, so we can talk about it later. No, that's just from group symmetry. I mean, if you write down here, sorry, I mean, whenever I put the chat. Okay, so how do I get to show my slide? I think when you couple this thing here, okay, when you couple the phonons, so the EG displacement to your nematic order parameter, from group symmetry, if I understand yours correctly, I mean, if you do have, I mean, I don't have I cannot explain that clearly here. It's just possible from group symmetry that you have a EG mode that couples to B1G fluctuations.
Okay.
We can discuss with Jorg. I mean, that's going to be my quick and dirty answer. Sorry for
Oh,
that.
my original feeling is that in orthorhombic phase, the EG will become, let's say, B2G and B3G, but they are still not B1G. So I think they are still, I mean,
No,
not
but
the.
okay, well, okay. This we can talk about it, but this is a different thing. I mean,
Sure.
if you talk, I mean the B1G in the orthorhombic phase is now called AG, so it's a different nomenclature. But just if you just take the tables of characters and look at what's possible, what symmetry couples to EG modes, just happened that the B1G does. That's
okay. So Ilya has a question. Yeah.
Yes, sorry, I cannot. I don't have a camera on this PC. Very nice talk, Matthieu. I have a question. So do I understand now right that you still don't know what is a primary order parameter in the system, right? Because initially in the stories that you put, you said, look, you know, this is a nematic liquid, but I missed to see, you know, the very nice divergence of the nematic susceptibility in the Raman data, which to me tells that you still don't know where the primary order parameter, also because somehow you left this triclinic transition completely apart, right? So there is a very nice story of the orthorhombic transition with charge density wave, but somehow what is surprising is that just few Kelvin below you have a triclinic transition, and you essentially don't know what is the origin of this triclinic transition.
No, that's correct. I mean, this is something we had a bit overlooked, but we're on it. So here's the thing, right? I mean, when you take the system and you start from the tetragonal phase and you start cooling it down, there are a few things that happen first. I mean, the first thing that we do see is the broadening of this EG mode, right? So that EG mode couples to something. Okay, that is appearing there, and then that thing gently develops, and then it develops alongside the I-CDW correlations, right? I mean, the I-CDW correlations are there. I mean, at the beginning, when you just do the basic X-ray diffraction experiment, you don't see them. Now, if you look more carefully with diffuse scattering, you actually see that there is this nice background of I-CDW fluctuations. And so those are here already from the beginning, and they gain in strength to the point that you form a long-range I-CDW order that then triggers an orthorhombic distortion. And as you increase the size of that distortion, then the system becomes triclinic, very, very brutally, I would say. Okay. So that's the sequence of the thing. Now, what we suspect is that what looks like a charge density wave is actually more subtle than that, right? I mean, and must have some kind of orbital polarization. So that's what we're trying to find out, but that's not so easy to be, you know, to find a probe which is, you know, orbitally resolved in this fluctuation regime.
Yeah, thank you very much.
So there's no thermodynamic evidence, right? Simon had a question, yeah.
Well, maybe you should finish your train of thought, Pinche.
No, I was just saying, I mean, for temperature well above the orthorhombic phase transition, there's no other thermodynamic measure. I mean, the signatures of.
I mean, what you have above is, let me get this. It's there is something weird going on along the C-axis. If you look here at the C/A ratio, the C/A ratio is increasing. So that means that as you cool, I mean, both A and C, you know, contract, but A seems to contract a bit faster than C. Okay, and at some point, so this is anomalies on its own, and then at some point this turns down. Okay, so then at some point you seem to accelerate the so either either you slow down the compression of A or you accelerate the compression of C. Christophe could comment better on that. But this happened to take place at a temperature which is very close to that temperature at which we start seeing the broadening of the Raman-Phonon.
Okay.
I think all those things are coupled. I mean, from the thermodynamic point of view, I mean, this is why Christophe called this fluctuation temperature. Okay, there's onset of fluctuations here, which matches very nicely the onset of the broadening, except maybe for this 10% sample, which is, I think, by far the most interesting, because here we don't have any trichonic transition left. We have the higher TC, we still have the CDW. There's no orthorhombic phase anymore, and yet we still have this big splitting and this fluctuation and everything, which starts from even higher temperature. So that is, to me, the most intriguing regime. And something happens here, which is also along the C-axis, some kind of collapse that we need to figure out what it is.
So, so I actually missed the Jean-Pierre's talk, so maybe a bit of study from scratch. So if I understand it correctly, there's no thermodynamic nematic phase transition, but there is static CDW order. Is that the correct statement?
There is something that looks pretty much like a static CW order, yes. And the nematic, I mean, there is an elastoresistivity signal that is associated with this buildup of the CW correlation, but there is no diverging electronic nematic susceptibility a la iron based.
Yeah, so that statement about elaston resistivity is actually interesting. But the question that was in my mind was that if the CDW is electronically driven primarily, I would, it seems to me that it would have more of the fluctuations, but if CDW is primarily driven by the lattice, then somehow my sense is that there will be less of the fluctuations of the CDW order parameter. So I wonder how much one knows about what is driving the CDW order, or is it at this point a well-posed question?
What we say is, again, we do see an instability from the first principle experiment calculation. So if you put the experimental crystal structure in your DFT calculation, or Olfai does it, and then he finds that it's simply unstable against the formation of I mean, there's a soft phonon, basically. I mean, a phonon which has an imaginary frequency. But the mechanism behind is a bit hard to identify, in the sense that it doesn't seem to be that you get, for instance, if you do the same thing for decalcogenides or any kind of Pyers-like system. It's not. You don't have this enhancement of a very strong enhancement of the electron-phonon coupling. You don't have a peak in the joint density of state at that Q, for instance, a good nesting, if you like. So from conventional CW-like thing, it doesn't seem to be the case, but still haven't really figured out what it is that forms this CW and what is, we call that a CW, but there's a good chance that is a bit of a different object.
Right. But is there, I wonder whether there's a way to look at the amplitude of this CDW order versus the lattice distortion, and does that give some empirical evidence one way or the other?
I mean, the lattice distortion is very, very small, but I mean, you do always have a coupling, right? I mean, I don't think it exists. It's possible to have a pure electronic modulation without the lattice to be distorted with it.
Sure.
But what's very clear is, I mean, and maybe it's already an answer. I mean, you see here from this thing, I mean, that distortion here is insanely small. I mean, it's 10 to the minus 4, and if you look at the CW peak, I mean, the superstructure satellites that we see in the X-ray diffraction, they are as intense as the nearby Bragg reflection. So for a very serious CDW, I would say you do have a very tiny lattice distortion. So maybe that already answers. So
if one wants to think, regardless of details, but if one wants to think of electronic interactions primarily responsible for driving this order, it seems to be consistent. Is that a fair statement?
Probably, yes.
Yeah. Okay. Thanks.
Do you have anything to say about? I mean, there's clearly TC enhancement, right, around 0.1. So do you have anything to say about in terms of the sort of nematic fluctuation versus TC as a Jean-Pierre's claim?
Not really, because No, I simply haven't really looked myself seriously at superconducting phase. I mean, to me, this is too low TC, and I again I got turned on with this.
Sure.
I got turned on with this Charncy wave story, and really, I wouldn't
Could it be
speculate.
Could it be just like BCS? I mean, in the sort of a doped compound. I mean, 0.1 somehow electron lattice coupling is stronger. I mean, that's where the thing is really interesting, right? If nematic phase is somehow associated with higher TC, then it's tremendously interesting, right?
Well, we had that discussion with Christophe the other day. I mean, if you look at the original paper by Alaska Subedi and David Singh, where they did the first principle calculation for that system back in 2008, they calculated the electron-phonon coupling, and they just found a TC of 4 Kelvin. Of course, there's always this instability, this uncertainty about mu star and everything. It's the right order of magnitude. So the highest TC that you get so far in the system is not really far from that you expect from the Macmillan approach, electron lattice coupling. So from that perspective, yeah, it might just be superconductivity might not be the most interesting phase of those systems. But that being said, I can't really, say more. It's more of a feeling, but one should really, I mean, what happens to the charge density wave in the superconducting state is actually something that I would be very intrigued about.
But along this sort of general direction, so maybe this is more of a general discussion, or maybe it's a subject of another talk, but this elastoresistivity that you mentioned, so first of all, is that in a B1G channel?
Yes.
And is that sort of increasing as you go towards increasing TC part of the doping?
Not really. No, I think it's no. I mean,
I think it disappears. I think the divergence disappears before. I mean, there's going to be a talk on this in detail talk.
I don't want to. I don't want to spoil this from the talk of Mehdi, but clearly,
we can leave for a few. We can live without it for a few minutes.
Thank you, sorry to.
Yeah, thank you, Matthieu, very much. Yeah.
Okay.
Yeah, very nice talk. Yes, thank you so much. Yeah. Any other question? Yeah. Okay, probably not. It's too late for him, so I don't want to.
It's getting late.
Yeah. Thank you, Matthieu. Yeah.
Thanks. Okay. Have a good day. And
bye.
see you around.
Bye.
Bye-bye.